Hello and welcome back to Calculus 1 section 3.9 on derivatives of exponential and logarithmic functions. Logarithmic, exponential, whatever. We'll do exponential first so, because that's easier and faster. And then we'll deal with logs. So here's the title. Exponential function. So exponential function is given as y equals usually a b to the x. That's some kind of general form. But for most of our application, we use y equal a e to the kx. That's what we use most of the time. You have seen that kind of formula used in your growth and decay problems, which is studied in Calculus 1. You will see them again in Calculus 2, differential equations. They're all over the place. So these are the most used where this is the general form. So whatever. Now, the question is derivatives, right? We know about exponential function. We know it's increasing. We know it doesn't have x-intercept. It has y-intercept at 1, and so all that good stuff. So the precalculus of exponential function still holds the same. The new stuff is that, and this is again from earlier in the semester, derivative of e to the x is e to the x, and then the derivative of e to the ax is a e to the ax, which you now know that you can deal with using the chain rule. So these are the two formulas which you memorized before and used it. And today we are going to do a little bit better than this. So we are going to focus on the derivative of e to the f of x. So if you observe these two, these are linear functions, right, in exponent. So it's just x, which is y equals x, which is just a 45-degree line, or ax, which is some kind of a slope line. So this is what we have for that. And then when you take the derivative, we know that derivative of e to the x is e to the x, so derivative of e to the f of x is e to the f of x, and then you multiply by the derivative over here. So you can now have the derivative of exponential function. And guys, this is the formula that you should memorize. So I'm just gonna do this. We use this, I'll just say all the time. All the time. You have a more general case, but the general case is almost never used, so we don't care about it as much. That's going to be b to the f of x. See, in this case, your base is not stuck to be e. It could be anything else. So you can have 2 to the sine x. You can have, 3 to the x squared plus 7, right? You can have anything. And you still have function in the exponent. So that's the general case. But again, the one above is the one that we use all the time, because 99.999% of the problems are always with e's. You really have to go out of your way to find problems that do not have e in it if you are working on application, right? So b to the f of x would be b to the f of x times f prime of x times ln of b. So this would be the general case. But as I mentioned, most of the time you will be dealing with the one in a cloud up there. So what is the derivative of e to the, let's say, cosine x? Well, if you follow the formula, you're supposed to copy the function as is, right? Because it says e to the f of x is e to the f of x. So that's the part where you copy the same thing. And then you take the derivative of the exponent. In this case, that will be negative sine x. And you're done. That's it. So the whole thing is negative sine x e to the cosine x. And then to give some application to this, if you remember the pendulum we talked about at one point, which will swing left and right, and we said that we're going to call the distance d e to the negative a t, and then let's say cosine omega t, where omega is angular velocity, which is how fast it's swinging side to side, and then that negative a t, that term negative a is the one that actually stops the pendulum from moving eventually. So we mentioned this briefly earlier. You are going to have the full lecture on this in differential equations eventually. Now, if I want to know the velocity, then that will be the derivative of the distance in respect to time, which means now I have to do the product rule, and then I have this term eventually that I have to take derivative of, which is so what do we have? We have d dt. So what I have now is the product rule. So copy the first, which is e to the negative at, and then copy the second. So sorry, copy the first, then derivative of the second. That will be negative omega sine omega t, plus copy the second, which is cosine omega t, times derivative of the first, and this is where our function up there, our derivative up there kicks in, which is we take negative a in front and then e to the negative at. So when you simplify, now velocity is going to be, you can factor out negative e to the negative at, and what's left is omega sine omega t plus a cosine omega t. And there it is. So this was product rule. Right? It was product rule. It was product rule. And we have the answer, we used the derivative of exponential in this case. So that was like the example number 2. We can also find the derivative of, let's do d dx again. Leibniz notation is really good because you can always tell what your independent variable is because you have it in the denominator of the notation. So you can, that's how we knew, by the way, because we took the derivative. Let me just go back to this problem. You see that the denominator says dt. That means that your independent variable for the problem is t. And you are taking the derivative in respect to t, which makes sure that a and omega are constants. The variable that appears in the denominator of the derivative notation is the variable for the problem. The other letters that you encounter in the problem are all going to be constants. So that's the reason why we treated this negative a and negative omega as constants, because the denominator there, dt told us that the time is the variable. Okay, so now I have the derivative of, and let's say you have 3 to the x squared plus x minus 1. So you have 3 raised to the polynomial. So try to use this formula with general base b to solve this derivative. So the derivative goes, we copy the problem as is, so 3 to the x squared plus x minus 1. Then we take the derivative of the inside, which is 2x plus 1, which is the exponent. And then we multiply everything by ln of 3. And now you can just make it pretty by writing the constant ln3 first, and then multiplying that by 2x plus 1, which is the linear term, and then everything times 3 to the x to the x squared plus x minus 1. There we go. And that's it about exponential functions. We don't have anything else. I hope you're not disappointed, right? You already know the basic e to the x formula. You might know e to the ax, but technically the one that you need to learn is e to the f of x. So whatever function ends up being in the denominator, whatever function ends up being in the exponent, right, you guys will have that formula most of the time. And whatever ends up as a function in the exponent, you take the derivative of that one as a chain rule. So that's all about exponential function. As long as you know the formula in a cloud, you should be 99% okay. The one on the bottom shows up on the exam, for instance, the math exam, but you're not going to see that one very often. It could show, let's say, pH calculations, maybe, if the professor is creative enough to put it up, because pH is done in base 10, not in base E. Also in physics, you talk about, let's say, scales to measure earthquakes. That's also base 10. So there are bases that are not E. That's why I said 99.999% of the cases, not 100% of the cases. But you can see this one obviously on homework and your lab and exam. But for purposes of education and later on work, most likely you will be using the cloud only. All right, time for logs. So, I don't need a password. So, first we are going to understand this is like 80% of the lecture is in logs. First, we need to review logs because some of you probably are not too good with them yet. And then we are going to learn something that is the most powerful technique to take derivatives that we know of. So let's start easy. 2 plus 3 is? There we go. We have a live one. Okay. Now, we can retrieve 2 and 3 by subtraction. So 5 minus 3 is 2, and 5 minus 2 is 3. So we have that. Then we have 2 times 3 is 6. And that would be multiplication. Multiplication is repeated addition, which is where you made the trade-off to memorize multiplication tables, so you don't have to keep adding. 2 plus 2 is 4, plus 2 is 6. You can just memorize 2 times 3 is 6 and be done. Now we can retrieve back 2 and 3 by dividing 6 and 3 to get 2, and divide 6 and 2 to get 3. Now we can push further. If you push further, you can now say, but we can have repeated multiplication, and those are the exponents. So 2 times 2 times 2 can be written as 2 cubed, which is 8. So now that's exponents, and exponents are fast repeated multiplication. So instead of writing 2 times 2 times 2, you would write 2 cubed, and that's going to be 8. Now, what we are going to do here is we are going to take the cube root of 8 to retrieve 2. How do I retrieve 3? Square root of 8 is 2 root 2. Cube root of 8 is 2. How do I get 3? Yes. Log 2 of 8 is 3. And that's where logs fit in. It's just a calculation. Just like addition and subtraction. You don't like it, obviously, because it has letters rather than a cute symbol. But at the end, you have two numbers that are input and a number that it's output, just like all other operations on the page, right? So logs fit in right there. And you can now see logs as arithmetic, not functions. Everything that you see here is just calculation. There are no any kind of functions on this page yet. Now I can create functions out of all of these if I involve variables, but none of them have variables right now, so they are all straight up calculations. So now when you think about operations that you have, mathematical operations, you have addition, subtraction, and their opposites. You have multiplication and division, and their opposites. And then you have exponents that have two different operations as opposites. They have roots, and then they have logs, right? So now you have the complete picture of where each operation fits. And you also hopefully understand that multiplication is fast addition, and then repeated addition, and then the exponents are fast repeated multiplication, which would make them, I guess, uber fast addition. I don't know, for the exponents. Anyway, now we can transform any of these into functions by replacing any of the input numbers with x. And depending which x you replace, you will create a different type of a function. So if you replace, let's say, 2 by x, you would get x plus 3, and x plus 3 is a linear function, right? You can replace 5 with x, get x minus 3, and you would get a linear function. You can replace 3 with x and get 2x and get, again, a linear function. You can replace, let's say, 3 with x, get 6 over x, and that's going to be, no, x over 6 would be linear. 6 over x is rational, right? It's a ratio, rational function. Then you can replace 3, get 2 to the x, get exponential function. You can also replace x and then have cube and have a polynomial. Then you can have your cube root of x, which would be a radical function because it's under some kind of radical. And then finally, we get to the one that we actually want to discuss, which is y equals log of some base a of x, which is called logarithmic function. So until the x creeps into the notation, you guys have exclusively calculation, right? All of that stuff up there is just arithmetic and nothing else. All of that stuff. Now, once you start replacing x's for any of the values, you get specific type of a function depending on where you place the x. And we see in the linear, rational, radical, exponential, polynomials over there. And then finally we got to the logarithmic function. So now, logarithmic function is going to be the focus of the rest of the talk. So now we start with the graph for the log function, right, which goes through 1. And we can write the specs for the log function on the side. Domain is going to be from 0 to infinity. You do not get to include any one of them. Range is going to be from negative infinity to positive infinity, which is going to be going all the way from negative infinity on y to positive infinity on y. And then we're going to have x-intercept, which is going to be at 1, 0. Then we're going to have the y-intercept, which is going to be none. We don't have. We do have a vertical asymptote at x equals 0, which is y-axis. And then horizontal asymptote, slant asymptote is none. We don't have any of those. So these are the basic specs of the logarithmic function. And all of this obviously is in your precalculus course. Now we want to also put down 2 special bases, because when I say log base a, you are allowed to put in any number for a, because that would just be, right, the base. Now what I want to do is I want to just briefly state that if you have a log with base e of x, we have the lazy notation for it. We just call it ln x. So ln x is nothing special. It's just the base is e, and then that log base e of x has a shorter notation. That's 2 characters shorter to write. So that's why we do it, because it's pretty much all of the logs out there are going to be natural logs because the base is e. So it's 2 characters shorter to write, so we just use ln instead, and then you are going to have the ln button on your calculator most of the time, right? If you're using your TI 83, 84, whatever, it's going to have ln button to press. If you have a base 10 on a log, so log base 10 of x, we just write no base. And if you encounter log without base, then that's going to be capital LOG button on your calculator. And you can find those buttons on the calculator. For, as I said, most used calculators are TI-83, TI-84. So if I just briefly bring up one of these, it doesn't matter. It's a terrible grainy picture. How about this one? Holy, come on, people, can you upload? Nice, large. There we go. So on the TI-83, 84, which are the standard calculators, you have your LOG and your LN buttons on the left. And again, LOG only calculates base 10, LN only calculates base E. Now you might say, well, what about base 7, right? Well, there are calculators out there that calculate any base because they give you log xy, right? So you can plug in anything. But again, those are not calculators. I mean, they are called scientific calculators, but the more sophisticated calculator is, less log buttons it has because you only need one button, either log or ln, because of something that we call change of base formula, which can be used to convert to any base for calculations. So this is for calculations. Generally, I don't think you will use this because no one in their right mind uses log base 7 anywhere, but I mean, we can, right? So log A, B. This is any numbers, A and B. It will be ln of B divided by ln of A, and also log base 10, so log B divided by log A. So this is called change of base formula, and that one helps convert the base. Now, this notation with log and ln is standard everywhere on all calculators and textbooks and so on, unless you pick up Wolfram Alpha. I don't know why, but Mathematica and Wolfram Alpha, they call ln log. So that's confusing as hell. And that's the only place where I found different notations. So when you are reading answers in Mathematica, let's say you did integration, you did derivative, you did something, right? So if you have any of those problems done in the Mathematica, answer will come out as log, let's say x, and for them that means ln x. So just maybe you might want to write the note, be careful with Mathematica and Wolfram Alpha if you're using their services for calculation. All right, so now, what would be the most important connection between exponential and logarithmic functions? And we kind of discovered that here when we talked about retrieving numbers, right? So if you carefully observe these two lines, you can write the conversion factor between the two worlds, world of exponential and world of logarithmic, and that is going to be this formula: A, B equals C converts into log of A of C equals B. So this is the formula that is important, very important, because this is the formula that is used to solve your logarithmic and exponential equations. If you have exponential equation, you have to convert it into logarithmic to solve. If you have logarithmic equation, you convert it into exponential to solve. So it is crucial to know this so you can solve word problems And again, this is something you learned in pre-calculus when you learned exponential logarithmic functions, when you did the word problems on decay, when you learned on growth, population, and all of that kind of stuff. So this is all old news. So technically, guys, everything we did so far was the review. And finally, we are getting to the 3 formulas that you will have to know in order to get through some very important derivatives. And these are the pre-calculus formulas that go like this: 1, 2, 3, right? So these are the 3 that you absolutely must know. Number 1, ln of x times y is ln x plus ln y. So if you have multiplication and the argument of ln, it can split into addition of 2 ln's. If you have quotient, it splits into what? Minus, yes, the subtraction of the 2. And finally, ln x raised to any power p, you can kick p in front of ln x. These formulas are going to be key for the rest of this section. And as I say, they are in the base of the most powerful the differentiation technique, which we are going to see in about 20 minutes, 15 or whatever. Now, before I jump into calculus, since we are still reviewing pre-calc, let's review the use of these formulas. So, your pre-calculus homework problems would say condense or compress, whatever, and then they give you 3 ln x plus 1/2 ln y minus 6 ln of z plus 1, for instance. So this is a standard pre-calculus problem, homework, exam, whatever. I always have this on the exam when I teach the course. And if you observe the formulas, you see that the 3/2 and a 6 all go as exponents of the argument inside. So your first step would be to put those inside as exponents. Now, you have the 1/2 exponent, and you know that 1/2 exponent is a square root, so you will put the square root of y. So we used rule 3 to get rid of all of those numbers in front. Right? This says condense into a single ln, so you are condensing all of this, right? And then addition is going to be multiplication, and minus is subtraction, is division, so we are going to have x cubed root y divided by z plus 1 to the 6. And this is the end of the problem. Your job was to take multiple logs and condense them all into one log. Now, these are obviously favorite pre-calculus problems because this is the skill you need to solve logarithmic equations. If you have multiple logs, you combine them into a single log, and that's equal to something, and then you can use the conversion factor to translate that into exponential, which you can solve, and then you're done, right? Now, calculus uses backwards procedure, which is expand. I put this one because that's the one that you need to practice the most, and that's the one that you will be using in every problem. So when it says expand, and then you are going to get, let's say, ln of x minus 1 to the 6th power times, let's say, sine x divided by the 4th root of x squared plus 1, for whatever, right? Just pile up whatever. It doesn't matter. Let's go x in front of the 4th root. How about that? Put the x there. So when you need to expand, you are going to use reverse steps. You are first going to separate this into 4 different logs, and then you will deal with exponents. 1, 2, 3, 4. So that's 4 different factors. So there will be 4 different ln's. So let's go and get them all. So this is going to be ln. This one is in the numerator, so it's a positive ln of x minus 1 to the 6th. The next one is in the numerator as well, so it gets a plus ln of sine x. The next one is in denominator, so it gets a minus ln of x. And the next one is also in denominator, gets a minus. It's in denominator. Yes, but it's in denominator. Right?
No, I know it's in the denominator.
Okay, so if you look at the formula, if something is in denominator, gets a minus.
No, I know that, but
It's as simple as that. If it's in denominator, gets a minus. If it's in the numerator,
I mean, like, they're both in the denominator, but
Good.
x is being multiplied.
So why would you discriminate against one and not the other if they're both in denominator? You clearly gave a minus to the first one. What's so wrong with the second one? Does it smell bad or something?
No.
No? Beautiful.
That's what I was
You can put parentheses around the whole thing, put it as a minus, and then you can distribute minus to both. Sure.
Always. Oh, okay.
Good, yeah. You can do that. If that's going to make you happy, right, then that's going to be like this, and you will have your plus because you want plus for the multiplication, but because they're both in denominator, the minus will distribute when you get rid of the parentheses.
Yeah, now I see.
Cool. That's why I added this one, because that's usually where the grade dies on the exam. So I make sure I have this as the example, so you guys ask that question, and then we clear it up in class, and then it's 100.
No, I liked doing it in high school.
Either way, it's fine. Just get it. Just yes.
I'm just doing my hair. I have questions.
No, you had your hand earlier.
Oh, yeah, before, but he said it.
Okay. So now all I need to do is to take those exponents 6 1/4, kick them outside, and we're done. So to finish it off, it's 6 ln of x minus 1 plus, there's no exponent on the sign, so just leave it alone. So sine x minus ln x and minus 1/4 of ln of x squared plus 1, and we are perfect. Now it would be the best if you could just do this mentally, to go from the top line to all the way to the last line, and if you are able to do that for logs. So let's go with the derivatives. So the derivative that you guys already know is that the derivative of ln x is 1 over x. So that's the one you already know. And it is also cool to immediately note that derivative of ln of ax is also 1 over x. So this means that the derivative of ln x is 1 over x, and then the derivative of ln of 6x is also 1 over x. So there's no, this a just magically disappears. Like, where does it go? Right? Well, if you use the formulas we just covered, it should be clear where it goes. So I'm going to erase the answer, and I'm going to put in the intermediate step that you can break the multiplication here into ln of a plus ln of x. And what's a? A is a constant. So what's ln of a? Yes, derivative of ln of a is 0. 0 plus 1 over x is equal to 1 over x, because this puppy over here is constant. So that's why ln of 6x is also 1 over x. Yes?
I thought we did like the chain rule stuff, it would be like a over x. Like ln, like let's say ln of 6x, wouldn't it be 6 over x?
It will be 6x, it will be 6 over 6x, and then 6's would cancel. Because when you're doing the chain rule, right, your denominator is no longer a single x, now it's ax. So then, so it will look like this: 1 over ax times the derivative of ax is a, and then these guys would cancel, giving you ax anyway. Okay, great. Perfect. So let's take a look at the formula that you absolutely must know if you're going to Calc 2. And that is the derivative of ln of f of x. So any function, it's no longer just x. Just like we upgraded e from e to the x to e to the f of x, now it's ln of f of x. And this is probably my favorite derivative formula, because you just go f of x as is. So literally Control C, Control V, all right? Just drop it in there, and then put its derivative on top, and you're done. You are going to be of this formula, whether it's a derivative or integral version. So, must know this. So I've been using this formula one way or another for the last 2 weeks or 3 weeks with both of my Calc 2s right now. So a lot of stuff will depend on you knowing this later on. Now, we know that ln is a special, right? ln log, because your base is e. And you might say, well, what if, we have any base, not just e. So there is a general form, but again, you have to be creative to get it right. Again, pH calculations, something about earthquake or waves, and very, very few applications for the general form. It says the derivative of log base, any base b, of any function f of x. All right, so that will be the general form. So you can have log base 2 of sine x, for instance. And the way it goes, it's the same as before. You will have your f prime of x over f of x, and then you will just have ln of b in denominator as well. So this is your general case. This is your general case, and you would calculate your logs. But again, the one that you absolutely must know if you are continuing your education, well, obviously it's going to be there on exams, at least the second exam and the final, the one in the cloud. But as I said, a couple of sections in Calc 2, later on differential equations and so on, will have that a lot. So make sure you know the cloud very well. So now let's take a look at the cloud. So what do I have? I have the derivative. This was on the exam maybe 2 years ago. This exact question. ln of cosine of x. It was either 4 or 5 points. It was a part A, part B question. Exam 2, I would say 2 years ago. And to use the formula, you copy the function as is in the denominator, and you put its derivative in the numerator. What's the derivative of cosine? Negative sine x. Very good. For a total of negative tangent x. So you simplifying this answer into negative tangent was an additional point. So if this was 4-point question, it was 3 points here and 1 point there at the end. If it was a 5-point question, then it was 3 and 2 or whatever, 4 and 1, whatever it was. So there you go. Let's take a look at derivative of ln of, let's say, square root of 1 over x. All right. So, can this be done in one step without too much sweat? And the answer is yeah, right? So what should we do? Beautiful. Square root is a half exponent. X is in denominator, means -1. So this problem can be rewritten as ln of x to the -1/2. And by the p rule, we know that we can kick this 1/2 in front of ln. So this is the derivative of -1/2 ln of x, which is you copy the constant, -1/2, and then you just take the derivative of ln x, which is 1 over x. So the answer is just -1 over 2x, and we're done. So if you can use those properties of logs, the three blue formulas that I listed, if you can use those, well, in that case, you guys are done quickly. Let me write those on the board so you can always see them. We have ln of x times y is ln of x plus ln of y. The next one is the one with division. Ln of x over y is ln of x minus ln of y. And the third one, the one that I used here, is ln of x to the p is p ln x. So your denominator, x in denominator, if it goes in the numerator, picks up the exponent of -1, and then square root is a half, so half times -1 is -half, so that's how it became x to the -half. Then by the rule 3, kick one -half in front of the ln, and then it becomes a constant. And when you differentiate, you get to copy the constant. So even if you do this the long way using the formula, it must simplify into this. If you did everything correctly, it will simplify into -1 over 2x. Cool. All right, so now that you are masters of these derivatives, and you studied the product rule and the quotient rule and the chain rule, and you know all of these kind of things, we can have some fun, right? Yeah. So the derivative of, and we have now x plus 6 cubed times the 4th root of sine x divided by, I can put something nice. How about x squared plus 6x minus 1 to the 9th? That's a nice example, right? When you look at it, it has everything. You have 3 factors in there, and each one of them on its own is a chain rule, right? But then you have a product rule conveniently in the numerator, and then the whole problem is actually the quotient rule, right? So the main thing is the quotient. When you have to take the derivative of the top, that will be the product, and anytime you take derivative of any of these, you have to do the chain rule because it's just so convenient, right? So this is one of those problems where you turn your notebook sideways and you kiss your next hour goodbye and then just, work it out slowly. You might get it, right? Now I'm going to sound like Morpheus from Matrix. What if I told you that you can take the derivative of this mentally without writing anything down and have the answer in factored form? Just like that. If you practice certain set of skills that you probably don't have now. You should, but you probably don't have them. If you practice certain set of skills, and no, unfortunately, you can't download them into your brain like Neo in the Matrix. You actually have to practice these skills. You would be able to just look at this, and not just this, any problem learned so far, you would be able to look at it and just say the derivative. That includes every derivative from the beginning of chapter 3. Cool, huh? Shall we? Yeah, why not? So we are about to learn something that is called logarithmic differentiation. My personal favorite. Logarithmic differentiation is a procedure that you learn and you grind through it to show the way it's done. But once you see the pattern between the answer and the problem, you can actually memorize the pattern, and that's where the mental derivatives kick in. Is everyone going to do it? Obviously not. But some of you who do learn this process, you can seriously freak out people in Calc 2, right? You're taking the derivative and writing the derivative down as professor is still working out writing the function. So that's like really, really cool. Well, it's cool in my neck of the woods. I don't know. Where are you from? So let's take a look at something simpler, right? The derivative of, let's say, x to the 6 times cube root of x minus 1 divided by cosine x. It doesn't matter, right? So it's much less writing than the previous example. You can have literally anything written down, what any exponents, any roots, doesn't matter, right? So how do we take these derivatives? Well, the title is logarithmic differentiation. You don't see any logs. That's the first issue, right? So we have to fix that. So the way this works is you write y equals, leave some space, and then you have your x to the 6 cube root of x minus 1 divided by cosine x. Now, why did you leave the space? To write in the log, exactly. So that's where the ln kicks in. And now you see why you need to be able to expand, right? You see the right side? It's just one giant mess of product rule and quotient rule and chain rule, right? What happens when you break them all into addition and subtraction? You kill all of those, right? And you just have addition and subtraction, which is easy to differentiate. So we are technically, with this method, we are killing the product rule, quotient rule, chain rule. We're just killing them all. So what do we have? We have ln y is equal to 6 ln x plus 1/3 ln of x minus 1 minus ln of cosine x. So I need you now to stare at the formulas on the board, stare at the function, stare at the expansion, make sure that everything is correct and understood. And that's the step that I need you to be able to do mentally if you want to take mental derivatives. That's the only step that you have to be really good with. Anytime you see the exponent, you know it's going to go in front of ln. So 1/3 is the exponent in front. There are no exponents here, so there's nothing in front of ln. These guys are in the numerator, they're all plus. How many you have in denominator, each one of them will have minus. So if you are able to mentally keep track of all of that and decompose this from the problem on top into the line over there, that is going to be the key for you to do these derivatives like that. So now, once I have everything expanded, I am going to take the derivative of the entire problem. So we are going to put d dx in front over here, and that is going to be what we have. Now we are going to use what we learned before called implicit differentiation. That was 1 over y. Keep talking. dy dx. Function of x, and because it's a function of x, we have to follow the chain. So that was our x in respect to x, dx over dx, they cancel. All right, on the other side, I have 6 times 1 over x. You see that this y needs to be transferred to the right side, so to leave dy dx alone because you are looking for the derivative. So now you have y times, and over here you have 6 over x plus 1 over 3 times x minus 1 plus tangent x, and all you need to do is to fill in y, but you know that y is your original problem. So the derivative of that monstrosity was very simple, actually, and we haven't done any of those rules. And that's the derivative. What's the next step from here? Well, what's the problem about? Are you going to look for a tangent line? Are you going to go and graph the function using chapter 4, set it equal to 0 for min and max? Like there are reasons. We're taking the next chapter, chapter 4, is going to be the one that determines what are the next steps. This is just take the derivative. It's the first step of the problem. So that is logarithmic differentiation, and what it does for us is it removes chain rule, removes quotient rule, removes product rule, right, and gets us to calculate these derivatives only using the basic ln formula here, where you copy the function, put its derivative on top, and just plow through everything. Let's take a look at another example. Say you have one of the old examples, let's say the product rule or something like that. So you had your x squared times e to the 3x. Now let's not use e now. Let's use sine of 3x. How about that? E cancels with ln, so that one has the special place. So now when you have this problem, right, you would label this as 3.4 product rule, and it is a product rule. But logarithmic differentiation can eliminate the product rule and just cast this into the basic form. Now, again, would product rule be faster? Yes. Product rule, to write out the product rule, it would be faster. But if you are taking these derivatives mentally, clearly it's not faster. Okay? There's a difference. Because when you do the product rule, you still have to factor at the end so that you can set it equal to 0 and continue with your chapter 4 calculations that are coming up in about 2 weeks. All right? Not 2 weeks. Next week, 4.1. Next week. What am I talking about? Well, unless, no, it will be 4.1, at least 4.1 next week, depending on when you pick your exam, if you pick your exam, whatever. This method gives us everything factored already. So, pick your poison. Standard stuff. Y equals, leave some space, x squared sine 3x. And then we put ln on both sides. Then we have ln y is equal to 2 ln x plus ln of sine 3x. You cannot break the 3x because it's buried inside the sine. So you just have to leave it like that, which is okay. At this point, you will differentiate both sides. So once you expand everything and you get your standard 1 over y dy dx is equal to 2 over x, because we have the derivative of ln x is 1 over x and then times 2, plus we know we are supposed to write sine 3x here. Derivative of this is 3 cosine 3x. We remember that trig rule with a's, right? So derivative of sine ax is a cosine ax. And this y will go to the other side. So dy dx is equal to y becomes our x squared sine 3x times 2 over x plus 3 cotangent 3x. Done deal. Done deal. Did we use product rule? No. We did not use product rule at all. Now, if you paid attention between the two methods, you notice that this deal of 1 over y is recurring, right? And you always have y times that parenthesis. So when you start, if you're interested in taking these derivatives mentally, you would start with, the first thing is to copy the function as is, and then you just have to mentally figure out what goes in the parenthesis. But what goes in the parenthesis comes directly from your ability to expand this mentally here. You would look at this and say that 2 will go in front of ln, so I just have ln of x, so that's 1 over x times 2, so 2 over x. Boom, good. And then there's times, which means it's going to be plus, and then I have to deal with this term. So sine 3x go in denominator, derivative of that is 3 cosine, so 3 cosine over sine is 3 cotangent, and you're done. So it can be done mentally as long as you can expand those functions in your head. Which now brings me to the problem that I posed before I even wrote the title. This thing. Right? You look at this and you go, holy nightmare. Right? Like, really? Take the derivative of this? Copy. Paste. There we go. So now this is my problem, and the steps to solve this problem are the same like for all others. You set this equal to y. You set this equal to y. You ln both sides. You expand everything, right? But then once you practice that enough, instead of doing all of that, you just write the answer. And the answer is always you copy the problem as is. So you have your x plus 6 cubed 4th root of sine x divided by x squared plus 6x minus 1 to the 9th. And now, parenthesis time. Now, it's good to observe and listen to connect the words with what's written, because you can always catch up writing in 1 minute. So this is, we're taking this derivative mentally. cube is going to go in front of ln. So I'm going to have x plus 6 in denominator. Its derivative on top is 1, and I have that times 3. Next one is times, which is, in my case, plus. A fourth root is a quarter exponent that goes in front of ln. I will have sine x in denominator. Derivative of sine x is cosine x in the numerator. Then the next term is in denominator, so minus, and then I have a 9 because that's the exponent, so minus 9, and then I have this long exponent, this long polynomial x squared plus 6x minus 1. Here it's derivative of 2x plus 6 on top, and there's the derivative. That's it. Cosine over sine you can write as cotangent. That's the only step. And you can factor out 2x plus 6. You can factor out 2 and make that 9 into 18. But you can't do much more than that. It's just cosmetical change. We are not changing problem fundamentally in any way. So that was taking the derivative of that insane problem just by looking at it. And it doesn't matter how complicated it is. If you ever went to those martial arts classes, they say the more opponents you have, the better, because you can use their momentum and their mass against them, right? There's the mathematical proof of that. Now you're going to go somewhere in some biker bar and get mangled. Anyway. So I'll go through the argument one more time when you're done writing. And then when you go home, obviously you can just write out all the steps, right? Y equals, put ln, expand everything, differentiate term by term, move y to the other side, and you're done. Ready? Let's go through the argument one more time. So the first part is to copy the question as is. So Control-C, Control-V, right? And then you look at the first one, has a 3 exponent. Because it has a 3 exponent, it goes in front. So that's 3 times, and then ln of this. Now, ln of that gets your ln of x plus 6. X plus 6 goes in denominator. Its derivative is 1 that goes up top, and then times 3 that came from the exponent, so 3 over x plus 6. Plus, because the next term is multiplied in the numerator, so plus. And then fourth root is a quarter exponent, and same thing, ln of sine x. So ln of sine x goes in denominator, its derivative cosine goes in the numerator. And then finally, minus, because this one is in denominator, minus 9. And then you have this in denominator, because you always copy in the denominator, and then its derivative on top, which is x squared is 2x plus 6, and then minus 1 is 0, right? And there you go. And now you can simplify a little bit. You can write cosine over sine as a cotangent. And then you can factor the 2 from 2x plus 6 if you really want to make that 9 into 18. But you can't really do much more than that. You do not want to find common denominators and multiply it with this and stuff like that, because your next step is to set it equal to 0. So you want factors. You want to set this one to 0 and this one to 0. When you set multiply, this one will that one would cancel, because when you cross multiply, 0 kills it and so on. So we don't care about denominators that much. Cool, huh? I know. So now is the time for you to go back to your problems where you had the quotient rule, the problems where you had, some chain rule, and then chain rule mixed with product rule, as we had it last week, to go and work it out. Also, what is the tangent line to this curve at x equals -1, right? Well, here's your derivative. Plug in -1 for every x. There's sine x there. That's going to provide us with some decimals, but that's okay. So you can find the tangent line by substituting x equals -1, which is what we did last class, right? You take the derivative. Once you have the derivative, you plug in the x value that is given to you, and then you have your slope. If the y value is not given, compute that one as well, and then you have your x, y, and m, and find b, and you're done. Another one? Yeah, why not? What else are you gonna do? Fine, you win. The derivative of, oh, let's do the weird one. 3e to the 4x divided by x squared times the cube root of x plus 1, whatever. All right, try that for some time. So this one is a little bit weird because of e. E cancels with ln, so the formula for the derivative doesn't work for that term. It works for the other two, but it doesn't work for e term. So what is happening for this problem? So now that you tried it, let's go and write y equals 3e to the 4x divided by x squared cube root of x plus 1, and then add ln. So we're going to work out this one in all the steps. So what I have is ln of y is equal to, and now I have ln 3, and the derivative of that is going to be 0, so that's just going to die. So I have ln 3 plus, and now I have ln of e to the 4x. And see, this is where they cancel, so this term is no longer ln, this term is just going to be 4x. Divided by, minus, these are in denominator, so minus 2 ln x and minus 1/3 ln of x plus 1. So now we differentiate in respect to x. We get our 1 over y dy dx is equal to, that's a 0, so that's gone. So I'm just going to do this. That goes to 0 when you take ln, and then these guys cancel. So derivative of 4x is just 4 minus 2 over x, because derivative of ln x is 1 over x, and then you have times 2. And then minus 1 over 3x plus 1, because the derivative of ln with x plus 1 is 1 over x plus 1, and then you have times 1/3. So now y dy dx is equal to, we have our original problem, which is 3e to the 4x divided by x squared cube root of x plus 1. That's our y. That has to go to the right. And now 4 minus 2 over x minus 1 over 3x plus 1. And that's it. That will be the answer. So ln and e would cancel up there, and that's the term that would not have ln in it, which is why we're getting this 4 as a constant there when you take the derivative of 4x. Yes?
I'm still kind of confused how you went from ln of 4x to just 4.
When I cancel ln and e, the term that stays is 4x. The derivative of 4x is 4. Right? Because I'm taking the derivative of ln 3, that's a constant, so the derivative of that is 0, that's gone. These guys canceled, so this term is just 4x. The derivative of 4x is 4. Derivative of ln x is 1 over x, and then you have times -2. So you're taking each one of those term by term. Better? Cool. Yes?
Why does ln of e cancel? Because he's a constant.
No, ln and e, they're inverses of each other. So they cancel. The rule from of logs, log a of a is 1, which would make ln of e equal to 1. Now if I have ln of e to the 4x, that's by p rule 4x times ln e, which is 4x times 1, which is 4x. There's that calculation as well. There's another one over here. Log of any base of 1 is always 0. These are, I call these cute formulas. They're there to help us when we need to calculate something. Anyway, That's it. That's logarithmic differentiation. We're going to take about 300-second break. And then when we come back, we'll talk about derivatives of inverse trigonometric functions. Bye.